So thank you guys for coming to the first statistical learning group of this semester. We're happy to have you here. We have way more people than our intro meeting, which somehow got caught in spam filters and was unable to reach the masses. So I'm glad to see there is interest because we were kind of doubting ourselves there for a little bit. Okay, so to start this off, a brief little background on why I'm giving this talk. I don't do deep learning research, so I'm sorry. During my internship at NASA this past summer, they asked me to check out deep learning for their problem, right? And it was still enormously above my head, of course, but it's actually quite accessible and it jives with a lot of major statistical ideas that you guys are seeing or have seen and are familiar with. So I investigated it a lot. I took pretty thorough notes, I think. I didn't end up implementing it. I ran some boilerplate code from the packages, but this is my opportunity to at least share with you what I found. So any questions at any time are welcome. I make no guarantee that I'll answer them in any suitable fashion at all. I reserve complete right to say pass and not return to it. But this is the Hitchhiker's Guide to Deep Learning. It's kind of the major greatest hits of, if you're on a roadmap of deep learning, what major sites do you expect to see? That's kind of stuff. So my hope is that after this, you could pick up a paper that has, deep learning in the title and at least recognize the names and know the general form of what they're trying to do with this problem. Who here has read Hitchhiker's Guide to the Galaxy? Okay. Well, then this joke will only jive with a couple of you out here. But when I started, looking into the deep learning stuff, I felt almost overwhelmed. And I was like, how am I ever going to learn this stuff? It's so recent, right, that I thought that, the only accessible point would be these very high-level academic papers. But what's great is because it's so recent, everyone's been putting things online. Like, there's a huge community out there that so many people are putting their code on GitHub. So many people are writing their own versions of things. There's a lot of resources. So my advice to everybody here is don't panic. We're going to be OK. The Hitchhiker's Guide to Deep Learning will give you the greatest hits. But here's some resources, particularly that I relied on. There's deeplearning.net. Who knew? And they're a little aggressive. They say something like moving past shallow machine learning since 2006. So shallow has become somewhat of a derogatory word to talk about machine learning architectures that aren't deep learning. And there was a major review paper by three big wigs in the deep learning field, LeCun, Bengio, and Hinton. That came out in Nature in just this past spring. And then there's also another review by Schmidhuber, Deep Learning in Neural Networks, an Overview. And then I found Michael A. Nielsen's book. He put online. It's completely free, but he's like, if you want to toss me a few bucks, I won't say no. Neural Networks and Deep Learning was also enormously helpful. And I borrowed a lot of the notation from that because I felt like it was really accessible. He did an incredible job. So this talk is essentially a boiled down version of these resources and a few other tidbits. And I'm going to put all these slides online. And notice these things are blue, so they're actually active links. So you can just pop open the slides and click to your heart's desire. So this starts off deep learning. I think a history is in order of how we got here. It starts off with something called the Perceptron. And I talked briefly about the Perceptron about a year ago in my other slug talk. And I said it sounded like a 1950s sci-fi villain. And I still stand by that statement. Or like a transformer, like the Decepticons. Like the major leader would be like Perceptron or something like that. But it's not quite that. Not super evil. So this is a picture of Frank Rosenblatt. I believe this was taken in the 50s. And his machine, or his team's machine, called the Mark I Perceptron. And the idea is that this little box right here is a whole bunch of photocells. And then there's crazy wires. Like, this is not the box. There's like wires. That's these things. And there's like a whole room type deal kind of thing. And what they want to do is basically classify objects and detect things, right? Now notice in the bag it says Perceptron. I have a hard time finding a very good description of Perceptron, but my understanding is that they would hold up shapes to the Perceptron and it would photo image it, and then based on on its classification algorithm, its very, very, very baby neural network in the background would try to say like, hey, that's a triangle, that kind of stuff. So Frank Rosenblatt really, He loved this thing. This was his baby. And he kind of got a little carried away. There's a New York Times article from, I think, the mid-'60s where he's quoted or at least insinuated that this is the beginning of true robots. Soon with the Perceptron, they'll be able to walk, talk, and even reproduce. And so there was actually a lot of people in the fledgling AI community that took issue with those statements, because they're like, okay, let's not overhype this, okay? But that was the kind of person he is. So this was the basic idea. This is called a single layer perceptron. You've got an input. It's some p-dimensional vector x, right? And all we're going to do, this should look familiar because it's pretty much what we do in regression all day long, is you attach some sort of weights to it plus some bias term, or what we're used to calling the intercept, right? And W is the vector of weights, and B is the bias term. And that's notation that's going to be consistent throughout this. So W is for weights, B is for bias. That should seem somewhat reasonable. And what they're trying to do is they're trying to classify X according to this rule. So if I hit the weights on X and then add B, if that output value is less than or equal to 0, I'm going to classify it into the 0 category. And if it's greater than 0, I'll classify it into the 1 category. So what they're trying to accomplish here is binary classification, right? And so, for example, if you had something like this, right, what you would want to try to do is, we know that these points belong to group 1. We know that those points belong to group 2, or group 0, if you want to say that. We want to find some sort of dividing line. We want to be able to draw a line that perfectly separates the two, right? And with the perceptron, what you're able to do is start off with some stupid line like this, right? And then wiggle it around, and it tries to converge to the point where everybody's perfectly classified, right? And so if we plug and play the single layer perceptron, it might come out with a decision boundary like this, right? However, here's the thing. There's a lot of variability from one single layer perceptron run to the next, because I could just as easily have ended up with a decision boundary like this, or this, or this. There's an infinite number of possibilities on the decision boundary. And so it's a little unsatisfying because there's not too much generalizability beyond a particular problem. And the main thing is it requires linear separability. It's only going to run until it converges to a point where everybody's in their own class and everybody's okay. If it's not perfectly linearly separable, it's just going to keep running forever, right? So for example, if you run into this problem, this was a classification task pointed out by Minsky and Papert in 1969. This is an exclusive OR function. Which means, the exclusive OR, usually in computer science, OR is, if at least one of them are true, it's true. Well, the exclusive OR says that, only one can be true and the other one has to be false. So for example, the points in the top right corner and the bottom left corner are true if you interpret, 1 as true and -1 as false. The 1 and -1. Sorry, the off diagonals are the true ones and the blue ones are the false. Try to linearly separate that with a line, and you'll quickly find that you hit some sort of blue screen of death. You can't do it, right? It's a very simple problem. This is all it is, right? And if your perceptron is going to walk, talk, and reproduce, but it can't figure out the pattern here, that's a major problem, right? And so, like I said, Minsky and Seymour Papert, they highlighted the fact that it's unable to learn that function, and they went on and on about how the perceptron really had a whole lot of problems. And the problem with this was that everyone was like, all right, I'm ditching out a perceptron world. It's not lucrative. It has some major issues. So primarily in the 1970s, even though there was a lot of excitement about the perceptron in like the late 50s and 60s, 1970s, people primarily jumped ship on perceptron research. Which is a bummer, but somebody came along and said, okay, sure, the single layer perceptron doesn't do very well, but how about something called a multi-layer perceptron? And what they're meaning here is a few different things. What it doesn't, a perceptron is like your particular binary classifier, cell. But what they're saying is, why don't we have multiple of those, right? So even though it's binary, if I've got multiple, I got a little bit more wiggle room. I can learn a little bit more complex relationships. The other thing is, why do we have to be stuck to this, binary classifier, this, 0, 1, 1 off, perceptron, we can be a little bit more flexible with that. So this is called the multi-layer perceptron, and even in some circles, you'll still hear neural networks called multi-layer perceptrons, but largely people have tried to move away from that term because these things don't necessarily use perceptrons anymore, and so it's somewhat of a dated term, but you may see it, and it may be in the context of just generally referring to a neural network. But you can do a lot more with this, and so suddenly, I mean, this came out, I believe, in the mid-'70s, but people were still like, no, I'm not going to touch that. But then around the '80s, there was a resurgence in the neural network research, and a big reason was instead of using a perceptron, which is this blue line here, which is that, it's either on or it's off, people started using, you'll notice that's the logistic function, or what people in this literature have come to calling it as the sigmoid. Now, this isn't the only sigmoid. You could do like hyperbolic tangent as a sigmoid. But this is generally when they say sigmoid, this is what they're referring to. And it gives you a nice, range between 0 and 1. You're not tied to I'm either 0, I'm either 1. You've got a nice spread. And so you can be a little bit more flexible in your classification tasks if you can give some degree of plausibility to, oh, I'm looking at this handwritten digit, and I think it's mostly a 7, but it could also be a 1 because they don't, that line on the top, that kind of thing. So the sigmoid gives you a little bit more flexibility. So the sigmoid was really good. It kind of lifted up the perceptron out of its grave, and then also people started trading multiple layers.